of the test. All right, welcome back everybody. We're at Lecture 17A, which really means there have been how many lectures so far? 32, because you get A and B. All right, yesterday we started with our angles and standard position, being able to go from degrees to radians, radians to degrees, learning where the terminal side of the angle is. We'll look back at that real fast. Then we're headed into Chapter 6, Section 2, and this course approaches trigonometry from the right triangle trigonometry, mostly because of the majors who take this course, forestry, etc. Right triangles the direction. If you were in Math 111 pre-calculus leading into engineering calculus, I believe that's a unit circle approach. But we'll sort of look at a unit circle when we start sketching our trig functions. There are lots of definitions of how we define our trig functions, and get that straight. We have some identities, all of these things to memorize to be able to apply. And the little extra that gets added in this section that is very important, and I don't believe this particular section asks you to do that, but that is an objective of the course, so be sure you're adding that to that, is finding the measure of the angle using the calculator. And so we'll have your calculators out ready to go. All right, and there's a good chance I think we'll be able to maybe start 6.3 in this particular lecture, and we will see. All right, any questions before we start? Are we good? All right, let me just ask you a couple questions about angles. Just as a quick review. What does it mean for an angle to be in standard position?
Along the x-axis.
The terminal side is along the positive x-axis, the terminal side. Excuse me, initial side. Initial side. Okay, and if I were going to look for an angle of 120 degrees, positive 120 degrees, where will I find the terminal side? Which quadrant? Remember your quadrants are 1, 2, 3, and 4. And the positive y-axis is like 90 degrees. The negative x-axis is 180. Negative y-axis is 270, and then you're back to 360, and you can just keep going round and around and around. So if you want to represent an angle of 120 degrees, your initial side's along the positive x-axis, and 120 degrees, the terminal side will be over in quadrant 2. Okay, what about if you have an angle of negative 240 degrees? Angle in standard position of negative 240 degrees. What does that negative tell you? Direction. We're going to be going clockwise. Clockwise. Okay, if we're going clockwise, once I get down here, I'm where? What's negative 90? Over here is negative 180, negative 270, and all the way over here, negative 360, and you can just keep going round and around and around. And negative 240 will send your terminal side where? To the second quadrant also. Okay, this represents an angle here of negative 240 degrees. Angle in standard position. Okay, the other thing that we talked about yesterday in the last tape was we can represent angles as degrees, and the other way we're going to represent angles is in radians. And a radian is just a real number measure as opposed to a degree measure. And you had a factor that we could use for conversion, knowing that pi radians is equivalent to 180 degrees. Or 360 degrees is equivalent to 2 pi radians. If you wanted to convert easily by looking at what 90 degrees is, well, if all the way to 180 is pi, well, 90 degrees is, what, pi over 2? And if you go all the way to 270 degrees, that's going to be pi plus 1 pi plus a half pi is 3 pi over 2. And 360 is 2 pi. Where would I find pi over 4? Pi over 4. Well, it would have to be halfway between 0 and pi over 2, right? So pi over 4 would be right here, pi over 4 radians. Okay. How many degrees do you think pi over 4 radians is? 45, because that's half of 90 degrees. What do you think pi over 6 radians is in terms of degrees? It is in the first quadrant. How about if I wanted to convert it to degrees? How do I do that?
180 over 5.
Yeah, we need to get it to degrees. 2 degrees. We would say at times 180 degrees divided by pi, because pi is equivalent to 180 degrees. And we're wanting to get units of degrees, so we need that up in the numerator. And the pi's are going to divide out. And 180 divided by 6 is 30 degrees. 30 degrees. Okay. What about pi over 3 radians? That's still in the first quadrant.
60 degrees.
Okay, 2 ways you could do that is pi over 3 is equivalent to what? 2 pi over 6, and 2 6 reduced to 1/3. So twice 30 degrees, twice 30 degrees would be 60 degrees. That's one way to do it, but that's not the way people generally do it. You could say pi over 3 times 180 degrees divided by pi. Pi's divide out. 3 goes into 180, 60 times. Okay, but the point I wanted to point out to you is pi over 3. If you know pi over 6, then pi over 3 is just twice pi over 6. So it's like twice 30 degrees. What do you bet 5 pi over 6 is equal to in degrees? What's pi over 6? You've already figured that out. 30 degrees. So couldn't I say 5 times 30 degrees? This is the same thing as 5 times pi over 6. Pi over 6 is 30 degrees. So it equals 150. But again, you could say 5 pi over 6 times 180 over pi. Just trying to get your attention here. Let's try another one. Partly because we're going to, in section 6.4, I think at 6.4, we're going to be looking at angles like 5 pi over 6 and etc. All right, so if we know pi over 6 is 30 degrees, and we know pi over 3 is 60 degrees, I just want to do this little quick drill here. What do you think 5 pi over 3 is in terms of degrees? Okay, this is the same thing as 5 times pi over 3. So it's 5 times pi over 3 is 60 degrees and be equivalent to 300. Okay, of course, you can always go 5 pi over 3 times, I want degrees, 180 over pi, right? Use that factor. So the pi's will divide out. 3 goes into 180 60 times. Is that right? 60, and 60 times 5 is 300. Okay, so you can still get that way, but I'm just trying to show you that if you have this reduced to lowest terms and you remember that pi over 3 is 60, you can quickly get to the degrees. Okay, everybody good? Where do I find 4 pi? I want to see what an angle of 4 pi radians looks like. Where's the terminal side going to be? Say it loud. It's going to be back to the positive x-axis. This is, if you go all the way around one time, you've gone how far? 2 pi. But I'm looking for 4 pi, so I got to go all the way around again. And there's an angle that measures 4 pi radians. Where is 5 pi? Okay, so this is 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So there's my angle that represents 5 pi radians. Well, how many degrees would that be?
180 is 900.
Okay, did you say 5 times 180? How did you say that?
I did 360 times 2 is 720 plus 180.
Okay, all right. So you could do a number of ways. 5 pi, you could multiply by 180 over pi using that factor. I realize what you did. You just went around twice and then added again. Pi's divide out. 5 times 180, 900 degrees. Okay, everybody good? Got that all straight? Negative degrees, positive degrees, radian measures. Oh, and the last little part about radian measure is, let's draw this again. If I'm in radians, I may not want to work in terms of pi's. What is pi divided by 2? 1.57 approximately. Pi is approximately 3.14. 2 pi is approximately 6.28. 3 pi over 2 is approximately equal, what, 4.71? What did I think it was 8? 4.71. Okay, so how would you represent an angle of measure 2 radians? Where would the terminal side be for an angle of 2 radians? If you start here, initial side along the positive x-axis, if you go up to here, you've gone 1.57. If you've gone to 3.14, you've gone too far. So this would represent some kind of angle of 2 radians. Let's switch that to degrees. What do I multiply that by? Pi over 180. I need the answer in degrees. 180 degrees over pi. So it gives me 360 degrees divided by pi, which is equal to, comes out to be, yeah, you're right, 114.59 degrees approximately. So that would represent, this angle represents about 114.59 degrees. Okay. The reason I did so much of this is sometimes students seem to think if it doesn't have a pi in it, it must be degrees. But pi is a real number measure, and pi can just be changed over to 3.14 or whatever. So when you see a number representing an angle such as 4, if you don't see a little degree symbol there, you have to assume it's radian measures. Some books will do 4 with a little RAD to alert you we're talking about radians, but I believe this book will just give you the radian measure, like 4. Okay? Everybody good? Alrighty. We are ready to go over all these vocabularies and definitions and identities from 6.2 and then apply it. Okay, so we're in section 6.2. 6.2. And the first thing we want to talk about is an acute angle. And I think you told me what that was in the last class. What is an acute angle? An angle less than 90, does that mean it could be negative 300? Okay, it's an angle between 0 and 90 degrees. An acute angle between 0 and 90 degrees. Okay, an acute right triangle. If it's a right triangle, it's going to be acute anyway. Yes?
Didn't you have an acute angle that's less than 0, but greater than negative 90?
If you had an acute angle in standard position, acute angle is, I think acute angle is defined between 0 and 90. I don't think it's, yeah, it is. You may be thinking about what is called a reference angle.
Yeah.
Okay, right. Acute angle is defined between 0 and 90 degrees. Bottom of page 610. Or if you wanted to be in radian measure, it's between 0 and pi over 2. If you're in a different quadrant other than your first quadrant, you're going to go for a reference angle. A reference angle is an acute angle between 0 and 90. Okay? Alrighty. If you have a right triangle, it would have to be acute in order for this to be 90, because what do let's call this angle alpha and this one beta. What's the sum of alpha plus beta equal to in your right triangle?
90.
Because all three angles in a triangle add up to 180. So alpha and beta together add up to 90 degrees. So each of those angles would have to be acute angles if you're in a right triangle. Okay, let me draw my triangle a little bigger here. Here's my angle theta up at the top. Here's my right angle. Where do I find my side, what is referred to as the side adjacent to angle theta? Would it be this side or this side? This one?
Uh-huh.
All right. What is the side opposite the right angle called?
Hypotenuse.
Hypotenuse. Always called the hypotenuse, opposite the right angle. So when you're talking about an adjacent side or opposite side, stay away from the hypotenuse because it has its own name. So if you're looking at an angle theta right here, if you want the side opposite it, just go right across, and here's your opposite. And then the other leg of your right triangle will be the adjacent side, okay? How about if I'm going to call this angle down here beta? Where is beta's opposite side? Right over here, opposite. And its adjacent side is right down here. The reason I'm saying this is because when you talk about the value of a trig function, you have to say with respect to what angle, because the opposite and the adjacents vary depending on which angle you're talking about. Okay? What are complementary angles? Okay? Complementary angles are two angles that add up to be 90. Two angles added together that equal 90 degrees. So what is the complementary angle for 30 degrees? Okay, the complementary angle for 30 degrees is 60 degrees because 60 plus 30 is 90. Okay, these two angles are called complementary because they will add up to 90 degrees. Okay? All right, let's get our definitions in. I'm not going to copy them on the paper because they're all right here in your book for you. We're on the bottom page 611. Can you see this? Okay, first, this is referring to figure 22 on page 611. I'll write the page here, just in case somebody's sound is not working on their video. Okay, we're on page 611, and our definitions here, all have to do with this angle theta being in this corner down here of the right triangle. So the sine, which is SIN, the symbol for SINE, and these are just definitions. Somebody decided to call all these things. The sine of this angle, sine is a trig function, is really a ratio of the opposite height over the hypotenuse. Opposite over the hypotenuse. All right, now when I do these, I like to say, okay, let me go from sine to cosecant. This is the symbol for cosecant. Okay, and this is written for you in the Word right above up here. Okay, cosecant. Notice that if the sine is opposite over the hypotenuse and the cosecant is defined to be the hypotenuse over the opposite, what is the relationship between the sine and the cosecant? Just a reciprocal, isn't it? This is equal to 1 over sine theta. So if you know the value of the sine, what the sine of the angle is equal to, then you're going to immediately be able to come up with the cosecant just by taking the reciprocal. Okay, the cosine of the angle theta, look at where your angle theta is. It says find your adjacent side and divide by your hypotenuse. Adjacent divided by hypotenuse. Now look at secant, S-E-C, secant. Secant is hypotenuse over adjacent. So what is its relationship to the cosine? What is secant? 1 over cosine theta. Okay? So if you know the cosine, then you know the secant. Okay, the tangent is defined to be the opposite side over the adjacent. The cotangent is defined to be the adjacent over the opposite. These are ratios. It's saying the ratio, the length of the adjacent over the hypotenuse. That is simply equal to 1 over tangent theta. Okay? All right, so let's take a problem here and use our definitions. All right, you have to memorize these in case you don't know them. Memorize. Okay? And of course you wouldn't be asked on the test, what is the sign where you have to put opposite over hypotenuse? You have to be able to apply the definitions. Okay, apply the definitions. All right, so here we go. Well, let's do it right here. Given this triangle, this is a right triangle, and I'm going to make this side 3 units and this side 10 units. We want to find the sine of theta, cosine of theta, tangent theta. And we want to find, I haven't shown you how to do this yet, the measure of angle theta. All right. Now once I know sine theta, I'm going to know what other trig function do I know right away? If I know sine, cosecant. If I know cosine, I know secant, and if I know tangent, I know cotangent. All right. Now this is a right triangle. My hypotenuse is opposite my right angle. I'm going to put my angle theta up here for fun. We're going to put our angle theta up here. How do I find out what my hypotenuse is? Okay, what's the name of that theorem? Good old Pythagorean theorem. It says that a squared plus b squared equals c squared, where a and b are the legs of a right triangle and c is the hypotenuse. So we have 3 squared plus 10 squared equals c squared. 9 plus 100 equals c squared. So what's c equal to? Okay, why is it not plus or minus?
Because you can't have a negative distance.
Because we can't have a negative distance here. So c is going to be the square root of 109. Okay? All right. For angle theta, what is the sine of this angle theta?
3 over 10.
Okay, remember sine is the opposite over the hypotenuse, so find your angle theta, go to the opposite side, which is 3, over the hypotenuse, which is square root of 109. You can put that in your calculator if you wanted to get approximately what that value is equal to. All right. You tell me that because you know the sine, the other function you immediately know is cosecant of the angle. And what is that? Square root of 109 divided by 3. Okay. Everybody with me? Okay. Cosine theta, here's our angle theta. We're looking for the adjacent side to this angle. The adjacent side is 10 over the hypotenuse, which is square root of 109. If you know cosine, you immediately know which other function? Secant. Square root of 109 divided by 10. Okay. tangent theta. We're working from theta. Tangent is defined to be opposite over adjacent. So we have 3 divided by 10. So if we know tangent, we immediately know cotangent, which is 10 over 3. Okay, what do your instructions on the test say? Given this piece of information, find the values of the 6 trigonometric functions. Okay, so we found the values of the 6 trigonometric functions. And basically that's just giving me a ratio of opposites over adjacents or opposites over hypotenuses or whatever. All right. Well, you would not be satisfied stopping here, which is all your book is asking you to do in this section. I can already tell that you would not be satisfied stopping there because you want to go, what is the measure of that angle theta? I'm very curious as to what the measure of this angle theta is. All right, if you look at your calculator, which probably does not look exactly like mine, you notice that you have a sine, a cosine, a tangent, sine, cosine, and tangent, somewhere on your calculator. And above it, you have a little sine with a -1, and a cosine with a little -1, and a tangent with a little -1. What kind of functions have we used when we use a little -1 up there? Inverse. Okay, this sine to the -1 does not mean 1 over the sine. You know, what a negative exponent. This means inverse sine, inverse cosine, and inverse tangent. All right, let's see how we're going to use this to be able to answer what is the angle. Okay, the question is find the measure of angle theta. The thing that we know is that the tangent of this angle is 3/10. The cosine of this angle is, but the question is, what is the angle? So what we need to do, and I'm going to pick the one that looks easiest that doesn't have a square root in it, is remember if 2 functions are inverses of each other, you form their composition and they sort of cancel each other out. So basically what I'm going to do is find the inverse tangent of both sides of my equation. Because this is really forming that composition there, so if you do the inverse of the function, don't you get theta? You get back what you would start with. So theta then is going to be the inverse tangent of 3/10. When you see inverse tangent of something, inverse cosine, inverse sine, this is saying, what is the angle? What's the angle? We're going for what's the angle. Okay. Now, the next little part you need to be careful on your calculator is, are you in radian mode or degree mode? So my calculator right above this button is a mode. You got a different calculator than me. Can I also look at yours? All right, I'm going to go to my mode button. And you'll notice on my mode button, I have radian measure and degree measure. I need to get it in degree if I want my answer in degree. So I'm just going to go down and get it on degree. And then for me, I just press enter. And so now I'm in degree mode. All right, so you always have to check, are you in radian mode or degree mode? Did you find that on yours? Okay, so now I'm going to clear out. I got to make sure I'm in the right mode. So inverse tangent, that says what is the angle where the tangent is 3/10. What is the angle where the tangent is 3/10? And you go, is this a number between 0 and 90? Better be, because you got an acute angle, right? And that is about 16.7 degrees. Approximately 16.7 degrees. It's going to be the measure of our angle. You know this is a small angle because this is a 3 and this is 10. The smaller angle is always opposite the shorter side. Okay. Now, if this angle right here is approximately 16.7 degrees, what's the measure of this angle going to be? Yep. Okay, it's going to be about a 73.3 degree angle. These two angles got to add up to about 90. So let's just do a little check. The tangent of 73.3 degrees. What should that be equal to? 10 divided by 3, right? It should be equal to 10 divided by 3, which is, what, 3 1/3? All right, we're going to be off a little bit because we've rounded here, but tangent of 73.3 degrees, 3.33317, so we're pretty close to 10/3, 3.333. And again, that's because we rounded that 3 right there. Everybody good? All right, let's try another one. Is everybody still punching away? You okay? All right. Let's see if I can make this hard. You ready for a hard one? Okay, hard. Hard. Okay, this is really hard. Are you ready for it? Okay, this is 30 degrees, and this is going to be 10. And I'm going to call this side A and this B, and I'm going to call this up here angle beta. All right, and we're going to want to solve for all the other parts of the triangle. Are you up for the challenge? Okay. In unison, I'm going to give you 5 seconds to think. Don't say it till I say go. What is the measure of angle B, beta? Go. You are so good. All right, so we know this is 60 degrees. How do you think we're going to be able to come up with side A? Okay, the first thing you noticed was, and I use words like this to help me think what I'm going to do. I'm given the angle. I'm looking for the side opposite. I know the hypotenuse. I hear angle, opposite, hypotenuse. Does everybody see my thinking process? Let me write it out in words. I'm given angle, looking for opposite side. I'm given hypotenuse. Which trig function? Okay, so your key words are angle, opposite side, hypotenuse. See how your thinking comes? All right, so what did you say involves an angle, opposite side, and hypotenuse? Sine. So what's my equation here? The sine of what? Sine of what? 30 degrees is A over 10. Now how am I going to solve this equation for A?
Divide by 30, multiply by 30.
Multiply 10 by the sine of 30.
Multiply both sides of the equation by 10, right?
Mm-hmm.
It's just like an algebraic equation. So A then is going to be 10 times the sine of 30 degrees. Okay, at this point we haven't memorized what some special values are. So be sure when you go to your calculator again, you always check your mode. Get in a habit of checking to make sure you're in the correct mode of your calculator, because you're going to get some weird stuff if you don't. All right, so always, let me write that, always check mode on calculator. All right, so we're there. All right, sine of 30 degrees. Okay, because we're in degree mode, when we put that as our argument for sine, it's going to tell us the sine of it. Okay, that's a 0.5 or a half. 0.5. Everybody see that on your calculator? So we have 10 times a half, which is 5. So A is equal to 5. Okay. Everybody good? All right, we're going to divide up and solve for B two ways. Solve for B. Okay, the line goes right between y'all over this way. I want you to solve for B using the Pythagorean theorem. I want you guys to solve for B using your trig functions. You've got the angle. You're looking for the adjacent. You know the hypotenuse. Which trig function are you using? Adjacent, cosine. Okay, go for it. I'm just trying to show you can't miss these problems. There's so many ways to work them. Did you get it? Are you not playing? Okay, we got it, everybody? All right, let's go with the Pythagorean theorem first. A squared plus B squared equals C squared. A is 5. Looking for B. C is 10 squared. B squared equals what? 100 minus 25. B squared equals 75. B is square root of 75. Are we good? Let's get an approximation for that. On the calculator, that's about 8.66. That's just so we can match up with what this side did over here. Okay, so that was one way. Now the caution for doing the Pythagorean theorem here is that if you had messed up finding side A, then you would have missed side B because you used something that you'd already made a mistake on. So normally I encourage you to only use what's originally given in the problem. You understand? If you missed that 5 there. Okay. So what was your trig function to find side B? Cosine 30 degrees equals B over 10. Multiply both sides by 10. 10 times cosine 30 degrees. You went to your calculator. We already know we're in degree mode. Cosine 30 is 0.866 something. Multiply that times 10. And B is approximately 8.66. Okay, so two ways to work in the same problem. Everybody good? All right. Let's continue with some more identities. More identities. Okay, and you just told me you're very good at the good old Pythagorean theorem. Go and call that angle theta. We'll call it adjacent, opposite, hypotenuse. Do you need to back up? Did I go too fast? Go ahead, I'm sorry. Let me back up.
Yeah, the cosine 30.
When you put that in your calculator, Did you get 0.866?
No,
I just need refreshing on how to know which to use if you know cosine.
Whether it was cosine or sine? Okay. Whoops, here we go. When you were looking for side B, you say to yourself, I have an angle. Say what's given to you. I have an angle. I'm looking for the adjacent side to that angle, and I know the hypotenuse. So if you use the words angle, adjacent, hypotenuse, that will send you to the trig function cosine by definition. Yeah.
When you do it for your variables on the bottom, like you had 10 over 8.
What do you do? Are we on a triangle?
I'm just saying, like, let's say it's sine, and like 8 over a is like the
8 over a.
Yeah.
Do you know the angle?
Yeah, like 30 or something like that.
Okay. All right. Let me make sure I got finished with Sarah first. Sarah, we good?
Yeah.
Yeah. Once you memorize those words, sines, cosine, or whatever, if you say what you're given, what you're looking for, you'll hear the words. Don't go away with your question. I want to drill you one more time on something else. I'm not leaving you yet. All right, suppose that you had information about this angle, say 40 degrees.
I was just wondering if you do use this thing. SOHCAHTOA for that.
Okay, yeah.
That's how you remember.
Okay, the way you memorized your sign, okay, the good old word SOHCAHTOA or something. How does it go? I forget. Sine.
Opposite over.
Yeah, SOH, COH, TOA, SOHCAHTOA. Yeah, some people remember that. I can never remember what it is. SOH for SOHCAHTOA.
It's an easier one too.
Do what?
It's an easier one too. Oscar had a heap of apples.
I like my way better.
I don't like your way. Oscar had
A heap of apples.
a heap of apples. What is that?
But then you just have to remember that it goes in sine, cosine, and tangent. So then
Sine,
it's opposite.
cosine. Oh, right here.
Yeah.
Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Soccer had a heap of apples. Yeah, I don't believe I had that one either.
Are you from Raleigh?
Uh-huh.
Well, I don't know why.
And your SOHCAHTOA.
Yeah, I could never remember that one.
Yeah, I wouldn't be able to remember that one. Okay. Yep, that's what it is. All right, but the other thing I wanted to, where was I? Right here? Before I did that? Just drilling on that a second. If this was 40 degrees and you were looking for A and this is 10, if you were trying to solve for A, you'd say to yourself, I'm given an angle. I'm looking for the opposite. I know the adjacent. So you hear angle, opposite, adjacent. What trig function are you using? Not sine.
Oh, I'm sorry.
Tangent.
Sorry.
Trying to confuse me. Tangent is A over 10. Okay, so listen to your words as you go through it. Okay, now back to Sam's question. He said, pretend that you have sine of 40 degrees, for example, is equal to 8 over A. All right. If you had a problem like 6 equals 3 over A, how do you solve that? Multiply both sides by A, so you get 6A is equal to 3, and then the next step is?
Yeah, but so when you put it in the calculator, it would be.
Okay. All right, so we'll go.
Like 40A.
All right, so cross multiply, right? Or multiply both sides by a, and you get a times sine 40 degrees equals 8. A is equal to 8 divided by sine 40 degrees.
I thought it looked weird with the degree sign, and I didn't know if...
It does look weird, but you're okay.
Yeah.
Everybody good? All right, we ready to move on? Okay, some more identities that you can have fun with. All right, so I've drawn my right triangle with angle theta. I'm calling this adjacent, hypotenuse, opposite, and hypotenuse for my angle theta. And we're going back to the good old Pythagorean theorem. A squared plus B squared equals C squared. And I'm just going to use these words for here's my A, B, C. Okay, so it would be adjacent squared plus opposite squared equals hypotenuse squared. All right? Now, the thing I want to do is go through and divide all the way through by hypotenuse squared. I want to divide by hypotenuse squared. So if I do that, I'm going to get adjacent squared over hypotenuse squared plus opposite squared over hypotenuse squared equals what? Hypotenuse squared over hypotenuse squared is 1. Okay? Now, you remember that if you had something like 3 squared over 5 squared, that's the same thing as 3/5 quantity squared. Isn't that the same thing? Properties of exponents. So adjacent squared over hypotenuse squared is adjacent over hypotenuse quantity squared. When you hear adjacent over hypotenuse, what do you think? Adjacent over hypotenuse? Cosine. Cosine of the angle squared. Plus, when you hear opposite over hypotenuse, what do you think of? Sine of your angle squared. All right, now notation has it that you don't write it as cosine of the angle squared, but that you write it as cosine square theta plus sine square theta equals 1. That's one of your first main trig identities. Cosine square theta plus sine square theta equals 1. Okay? Trig identity. An example. Suppose we wanted to find the cosine square of 73 degrees plus sine square of 73 degrees. Well, the identity tells us that's equal to 1, doesn't it? But let's check it on the calculator. I'm running off the bottom of the page. Okay, I'm in degree mode, so I'm going to look at the cosine of 73 degrees. Cosine of 73 degrees. And then I'm going to square it. Where's my little square button on here? Cosine 73 degrees squared is 0.0855 approximately. Okay, now we're going to do the sine of 73 degrees. And I'm going to square that. And that comes out to be approximately 0.9145. And when I add that to 0.0855, it's going to come out, I hope, pretty close to 1.000187. I'm off some due to rounding. Okay, but the identity says that anytime you square the cosine of an angle and you square the sine of that very same angle, it's going to add up to 1. Okay, it's called, that is a main trig identity, and that's on page 6 13 in your book in case you're looking for it. Okay? All right, you then have two other identities, and sometimes you're using these identities to help you find the values of trig functions.
Use that in like a question. As to what would the question be like that you would know that you to apply that?
Okay, what would the question be that you would use that in? Okay, let's see if we can find one. I'm in the exercises on page 620. 620. Number 37 on 620. That's a direct identity right there. Okay. The other thing I want to tell you where it says use the definition or identity to find the exact values. For a problem like number 25, if you wanted to use the identity for number 25, you're told that the sine of the angle is equal to the square root of 2 over 2. If you wanted to find the cosine of the angle using the identity, you know that sine square theta plus cosine square theta equals 1. So in this case, we're given that the sine is square root of 2 over 2, and we're going to square that, plus cosine square theta equals 1. What's the square root of 2 over 2 squared equal to? Okay, that would be 2 over 4, which is a half, plus cosine square theta equals 1. Cosine square theta equals 1/2. So the cosine of theta is really plus or minus the square root of a half. And then if it's an acute angle, you could only go with the positive. Okay. Of course, you also could have an angle between 270 and 360. Later we'll get to solving trig equations, but right now it would be a half if you were talking about an acute angle. Okay, so you could have used, all right, so there was two ways to do like this problem number 25. This is using the identity, or it said you could use the definition. So here's your angle theta. It says the opposite over the hypotenuse is square root of 2 over 2. Opposite over hypotenuse. Do you see that? So if you draw your triangle, the opposite over the hypotenuse is the sine of the angle. So now you could use your little Pythagorean theorem and come up with this side, doing a squared plus square root of 2 squared equals 2 squared, and it's going to get you right back down into here. Okay, is that good? All right. Okay, so now there are more trig identities you get to memorize, but if you see where they come from, it makes it a lot easier. Sine square theta plus cosine square theta equals 1. All right, I'm going to give you 30 seconds to come up with the next one. I want you to divide all the way through by sine square theta. I want you to divide each term through by sine square theta and simplify. 30 seconds. Go fast. I'm watching the clock. Divide through by sine square theta. I'm partly watching the clock because the tape's about to run out. I just got the signal. All right, if I divide sine squared by sine squared, that's equal to 1. Cosine over sine is cotangent, and we got a square there. And 1 over sine is what? 1 over sine is cosecant, and we'll have that squared. Cosecant square theta. I'll pick that right up at the beginning of the next tape, okay? All right, we got to quit. We're running out. All right, go take a break, everybody. Alrighty, welcome back. We're at Lecture 17B, and we're going to try to finish up section 6.2 with some identities we were working on at the end. We're going to press forward through section 6.3. We're going to have some special angles that we're going to want to memorize the trigonometric values for. They're called exact values for some of our special angles. So that'll give you something over the weekend to do on Saturday night. Thought you'd appreciate that. And then we're going to look at some applications of our right triangles, and this is also covered in Chapter 8, Section 1 of our textbook. So hopefully we get through all of these wonderful things. Okay, at the end of 17A, we were looking at some more trig identities, and we had 30 seconds because the camera was about to cut me off. And I asked you to go through and take this identity, sine squared theta plus cosine squared theta 1, and divide each term by sine squared.
Can I ask a question?
Yes.
How did you come up with how did you get cotangent and cosecant from? Where is that at?
Okay. So his question was, how did we get that right in the last few seconds of the last tape? All right, if we divide all the way through by sine squared theta, you agree that sine over sine is 1, and then 1 squared is 1. Okay, when you hear cosine over sine, well, you may not have recognized where that came from now that you ask. So here we go back. Okay, when you looked at back on page 611, we defined tangent to be opposite over adjacent. And the little formula that and so I'm so thankful you asked me, I really do appreciate that, is that when we have the definition that the tangent of theta is opposite over adjacent, you'll recall that if you had opposite, that gets back to sine, where sine is opposite over hypotenuse and the adjacent is coming back to the cosine part. So what I want to do is just kind of show you that if we say sine divided by cosine, where sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. Okay? All right, we have a complex or compound fraction here, so if I invert and multiply, the hypotenuses divide out. So opposite over adjacent is equal to tangent. Therefore, tangent is equal to sine theta over cosine theta.
Okay, so it was cosine, so it was cotangent.
Exactly. And so let's do that. I'm so sorry I forgot to do that. Cotangent theta is defined to be, as you know, 1 over the tangent of theta, because they're reciprocals, right? And 1 over the tangent, well, let's see, how do we want to do it? If you do opposite over adjacent is tangent, it would be 1 over opposite over adjacent, which is adjacent over opposite. Does that help? Okay, so that also means that if you go backwards on this, it is going to tell you that that is going to be cosine theta over sine theta, because tangent is sine over cosine, cotangent is 1 over this. Okay, thank you. That was kind of an important point I left out, wasn't it? All right, so now, did everybody get that? Was that too fast, too slow? We're perfect? All right. So when you get cosine over sine is cotangent. So we get cotangent squared, and then 1 over sine is cosecant. Okay? 1 over sine is cosecant. All right, lots of little identities in there. Okay, that's number 2 identity that you want to memorize. And let's go, this is number 2. Let's go for the third one. We have sine square theta plus cosine square theta equals 1. In the first example up here, you divided through by sine square. What do you bet you're going to divide through this time to come up with another identity? Cosine square. So now go through and divide by cosine square theta. So we'll take every term and divide by cosine square theta. Okay. All right, now we have sine over cosine, then of course it would be squared. This is the same thing as sine theta over cosine theta squared plus cosine squared over cosine squared is 1 plus, equals 1 over cosine of theta squared. Okay, so now when you hear sine over cosine, you're thinking tangent. So we have tangent square theta plus 1. And when you hear 1 over cosine, you think secant. And we have secant square theta. Okay? Is that good? All right, and these identities can be used to help you find values of other trig functions. If you know one, you can find another. Or you can go right to your little right triangle and put it in to find some of your other angles. Okay, so various ways you can do it. All right. These identities are on page 613 in the bottom of your book. Page 613, bottom of the page. Number 6 was tangent square theta plus 1 is secant square, and 7 is cotangent square theta plus 1 equals cosecant squared. All right. At the top of page 614, I think they just sort of put them all together for you. Tangent sine over cosine, cotangent cosine over sine. I just always remember that cotangent's 1 over the tangent. I always work from sine, cosine, and tangent. If you got those 3, then you can easily get to the other 3. Cosecant being 1 over the sine, secant theta being 1 over the cosine of that same angle theta, cotangent theta being 1 over the tangent theta. And then there's those 3 identities. And they have you play around with some of these using some of your identities. And you've got a lot of examples. Just call this fun and games. When you see sine 20 degrees over cosine 20 degrees, your brain's going to go sine of an angle over cosine of that same angle is tangent of the angle. So that's equal to tangent 20 degrees. So tangent 20 degrees minus tangent 20 degrees is 0. They're just having you play with some of those. Okay? All right. I think we have really covered everything pretty much that you need to work on this. So let's get started. I'll back up on lecture 18 if we have some questions about that. Let's go to 6.3 so we can move on. 6.3, we're going to have some special angles. Special angles. All right. And what's really interesting is there are a few angles that have exact values. The trigonometric functions, you have the exact values of these special angles. And these special angles are 30 degrees, 60 degrees, and 45 degrees. 30, 60, and 45 degrees. So we're going to start out with the 45 degree angle, and we're going to come up with the sine, cosine, and tangent of the 45 degree angle. Once we know the sine, cosine, and tangent, then we immediately know all the other secant, cosecant, and cotangents of those. All right, and the way I'm going to derive this for you is I'm going to set up a right triangle, because sometimes if you see where this is coming from, it makes it easier to remember. And if this angle here is 45 degrees and this is a right triangle, what's the measure of this angle up here? 45. What kind of triangle do you call this when you have two angles with the same measure? Isosceles. So this is an isosceles right triangle. Okay, what do you know about the sides, the length of the sides opposite those angles that are the same? They got to be the same length, right? Because the angles are both 45, that means the length of the sides have to be the very same thing. All right, so I can make this any number I want for my right triangle as long as they're the same. So I'm going to be lazy and just make them 1. I could make them 3 and 3, 25 and 25, 112, 112. Make them whatever I want. They're just going to be the same. All right, then I'm going to use the Pythagorean theorem to find the hypotenuse. 1 square plus 1 square equals c squared. 2 is equal to c squared. C is equal to positive square root of 2 because we're talking about the length of a side. Okay? All right, so we have the cosine of 45 degrees, the sine of 45 degrees, and the tangent of 45 degrees. All right, so it doesn't really matter which of these angles I'm working from. I'll just work from the one in the lower left. The cosine of 45 degrees is 1 over square root of 2. Now that is a perfectly wonderful answer, but because this has been around for hundreds of years, and everybody before the days of calculators had to rationalize denominators because it was easier to work with, tradition has it that you rationalize this, meaning getting rid of the radical in the denominator, and you get square root of 2 over 2. This is what everybody seems to memorize as the exact value of the cosine of 45 degrees. Okay, the sine of 45 degrees, opposite over hypotenuse, is the same deal, square root of 2 over 2. And what is the tangent of 45 degrees? Tangent of 45 degrees? 1. All right, so let's make up a problem. I'm thinking as I'm turning the page. All right. This is the easiest one to memorize. Is the cosine of 45 and sine of 45 are both square root of 2 over 2, and the tangent's 1 because tangent is sine divided by cosine. Sine divided by cosine. The only way you're going to get a 1 is for the sine and the cosine to both be equal. Okay. We're going to have a tree. And we're going to have a shadow here of 100 feet. And the angle from the shadow to the tip of the tree here is 45 degrees. Somebody's measuring this. All right, and the question is, how tall is the tree? How tall is the tree? That one's a little bit too easy. But we want to do this just like we normally do. I'm given an angle. I'm looking for side opposite. I know the side adjacent. So I have angle, opposite, adjacent. What trig function? Tangent. Tangent 45 degrees is equal to the height of the tree over 100. This is the one you're going to memorize. The tangent of 45 degrees is 1. You already knew this answer before we did it because it's an isosceles right triangle. My tree is straight up, okay, over 100. So the height of the tree is also 100 feet. Okay, if you want to call that an x, x is equal to 100 feet. Okay, so there's your application. All right, tell me what the radian measure is for 45 degrees. Okay, so you can either quickly figure it out by multiplying like this, which is pi over 4. Or you can remember that 45 degrees is halfway between 0 and pi over 2. So half of a half is a fourth. Okay? All right, so turn to your neighbor and tell them the sine of 45 degrees. Say it. Look at your neighbor's face on. Turn and look. Tell them what the tangent of 45 degrees is. Don't tell me, tell your neighbor. Ask them if they're going to ever forget it.
Yeah.
No, you won't. Okay. Tell them the radian measure for 45 degrees. Pi over 4. All right, so we're good and experts in pi over 4. Now let's work on the 30 degree and 60 degree. So we're going to derive it. And the reason we're deriving these is because you need to know they didn't fall out of the sky. And also sometimes when you're in a situation and you can't remember, if you at least saw how it happened, you may be able to come back with it. All right, so I'm going to set up a equilateral triangle. What's an equilateral triangle? All sides are equal. What does that mean about the angles then? They're all equal. What would that be? 60 degrees. Y'all are good at geometry, right? Okay. If this is an equilateral triangle and all sides are the same, I can pick whatever unit I want it to be. And so being lazy, 1 is always a nice, easy number. Okay? All right. There is a theorem in geometry that I'm hoping somebody's going to quote for me that says, if I bisect this angle of an equal angle triangle, equal angular triangle, okay, it's going to come down and be perpendicular over here. And what does it do to this side?
Splits it in half.
Splits it in half. Can you quote the theorem?
It bisects it. I don't remember how to quote it.
I was asking you because I couldn't remember the exact words myself. Okay, it's something about if you have an equal angular triangle and you bisect this angle, it also drops a perpendicular and bisects the other side. There's a theorem in geometry about that. Okay, so if I bisect this angle up here, it now is a 30-degree angle. So I'm just going to pull this little part of the triangle off and look at it closely. Okay, so here's my 60 degrees. This is my 30 degrees. This is a half, and this is 1. Okay, I can find this side right here by using the good old Pythagorean theorem. Call that a b. So 1/4 plus b squared equals 1. B squared equals 1 minus a fourth, which is 3/4. So b is going to be square root of 3/4, which is square root of 3 over 2. Square root of 3 over square root of 4. Square root of 3 over 2. Okay. Which number is bigger, square root of 3 over 2 or a half? Which number is bigger? Wasn't square root of 3 1.732?
I don't know.
You don't know the square root of 3?
Square root of 3 over 2 is big.
Square root of 3 is about 1.732. So is 1.73 over 2 bigger than 1 over 2? Yeah. Okay, the reason I'm asking that is to prompt you again. Opposite the 60-degree angle is the bigger side. Opposite the 30-degree angle is the smaller side. Things are clicking. Okay. All right. Square root of 3 over 2 is bigger than a half. All right, so now we're ready to go with our exact values of these trigonometric functions. Let's go for the cosine of 30 degrees, sine of 30 degrees, tangent 30 degrees. All right, cosine of 30 degrees. We're up here, 30 degrees, so adjacent is square root of 3 over 2 over 1. The sine, the opposite over hypotenuse, a half. What's the tangent of 30 degrees? Tangent of 30 degrees. Tangent sine over cosine, you get 1 over square root of 3, and tradition has it that you rationalize that denominator and get square root of 3 over 3. 1 over square root of 3 is just fine with me, but a lot of times you'll see square root of 3 over 3. Okay? Let's look at cosine 60 degrees, sine 60 degrees, tangent 60 degrees. Now you do realize that 30 degrees and 60 degrees are just complementary angles, right? Complementary, they add up to 90. So basically what's going to happen is the cosine of 30 degrees is going to become the sine of 60 degrees, okay? All right, so the cosine of 60 degrees, remember 60 degrees is the big number. So the side opposite's got to, cosine's adjacent. 60 degrees, so the side adjacent's got to be small. 1/2 over 1. Sine 60 degrees, the opposite's got to be the big number. Square root of 3 over 2. And the tangent is square root of 3. Okay, the cosine of 30 degrees is equivalent to the sine of 60 degrees. Sine of 30, cosine 60. Okay, they're complementary angles. Yes?
And so then, isn't it going to be like when you have, say, 5 pi over 6, it's still going to be sine is 1/2, the cosine is square root of 3 over 2?
Yep, because we will be using those for reference angles.
Okay.
Yep. A little bit of knowledge makes you think ahead. I think that's section 6.4 we'll be getting to. Yep, we'll be using these later. All right, the next thing we need to do is make sure we also have the radian measure. 30 degrees, who recalls what that radian measure is? Pi over 6. 60 degrees, what was that one? Pi over 3. You know how to derive these if you forget? And what was 45 degrees? Pi over 4. Now, everybody has silly ways of remembering things. Anybody got a way to memorize these pretty easily?
No, I just
You just know them.
It's how to derive them.
Well, my silly way is that I've only got 3s and 6s, and I just never put the 3s with the 3s and the 6s with the 6s. So if it's 30 degrees, I know it's got to be pi over 6, and if it's 60 degrees, it's got to be pi over 3. That's the only way my brain works to remember that. All right. Now, what about memorizing these trigonometric values? My focus is always to go to the sine of the angles, because I think in terms of sine being the opposite, so if I got a little 30-degree angle, the opposite's got to be the little number. There's the half. If I've got sine of 60, 60 is the big angle, so opposite it's got to be the big number, the square root of 3 over 2. And once I take care of my sine, then I know my cosine and tangent work out okay. All right? Everybody hanging in here? All right, I'll show you where this is in the book, page 625. They set up a little chart for you. And it looks really awful when you first look at it. They give you the radian measure of these special angles. They give you the degree measure. And all we did was the sine, cosine, and tangent. Because I claim that if you've learned the sine, you immediately know the cosecant. And if you get the cosine, you immediately can figure out the secant by taking the reciprocal. And if you know the tangent, flip over the tangent and you come out with the cotangent. So I say don't run your brain crazy. Just learn your sine, cosine, and tangent, and then you can work from there. Is everybody good? All right, now your textbook authors give you some drill and practice on these. Just by giving you some of these expressions. What do the instructions say so that you don't miss this on a test? Exact value. When you're working with exact values, that's mean stay away from the calculator. We want the exact values. Don't give me any calculator approximations. Exact values. Okay? How's that, good? All right. Let's work a couple problems. Let's see. I wanted to go to page 633, number 64. Probably a WebAssign question. All right, so you know you're supposed to memorize all that stuff. We're on problem number 64 on page 633. Page 633. Statue of Liberty. We have a ship that's just offshore of New York City. A sighting is taken of the Statue of Liberty, which is about 305 feet tall. The angle of elevation to the top of the statue is 20 degrees. How far is the ship from the base of the statue? All right, we have these words that are called angles of elevation and angles of depression. Angles of elevation and angles of depression. If I keep looking, I'm seeing more words with angles of elevation all over the place. So I'm going to tell you an easy way to remember what these words mean. All right, angle of elevation. First thing you're going to do is think about your eye. This is a person, and here's the eyeball. Okay? So when you're doing angle of elevation, it's always from the eyeball, wherever the eyeball is. Okay? So you just imagine, if they're talking about an angle of elevation, you put your eyeball wherever it says. Okay, so your eye would like to look straight. Now, if I tell you to elevate your eye, which way is it going to go? Elevate. Up. So you're going to go like this to elevate. So the angle of elevation to the, say, top of something is this angle right here. Okay? Now, pretend that you're on the top of a mountain and you see something down here on the ground. Your eye would like to go straight out. The problem will say the angle of depression to the person or point on the ground. So if your eye is this way and you want to depress your eye, I guess, what's it going to do? To see this object, it's going to have to go down. This angle right here is called the angle of depression. Okay? All right. Everybody got it? So let's practice with your eyes. Everybody look straight out. I hope the camera's focusing in on some of these people. Everybody look straight towards me, and I want you to elevate your eyes to the top of the room. All right, you got the angle of elevation. It's between the horizontal, where your eye was looking up. Okay, be sure you get the people who are looking down. Got it? All right, angle of elevation, your angle eyesight, and you want to depress, what are you going to do? Go down. Got it? Can't ever miss it again. All right, so here we go. Let's work on problems on page 633. Number 64. We got to draw our ship. We got to draw our Statue of Liberty. We know how tall it is. We know the angle of elevation to the top of the statue is 20 degrees. So that means you are going to put your eyeball on the ship. All right, so here's the Statue of Liberty. I hate to even try to draw that. All right, here's the Statue of Liberty. All right. Are they holding something? All right. Sorry, torch. Oh, wait, it's over here. That's bad. Okay. This is really bad. All right, Statue of Liberty. Okay. It's 305 feet tall. Okay, over here we have a sightseeing ship. That's a sailboat. Okay. All right. The eyeball is right down here that would like to look straight across, but the angle of elevation to the top, so the eyeball is looking this direction, but we elevate, so it goes up to here. Elevate 20 degrees. That looks like more than 20 degrees. Okay, not quite drawn the scale. The question is, how far is this ship from the base of the Statue of Liberty? We'll call that X. How far is it? Okay. All right, what's the words you're using so you know what trig function to use? You're given a angle. You know the opposite. You're looking for the adjacent. Angle, opposite, adjacent, and everybody says tangent. So we have the tangent of 20 degrees equals 305 over x. Sam, this problem must be just for you because you asked about that first thing, didn't you? All right, so we're going to solve for x by multiplying both sides by x. X can't possibly be 0, right, to have a 20-degree angle of elevation there. So x, that's why we can multiply both sides by x. It's not 0. So x then is equal to 305 over tangent 20 degrees. All right, this isn't an exact value problem. I don't know why it was, I thought we were doing only exact values in this section, but we can work the problem. When you go to your calculator, what are you going to remember to do immediately before you plug in a 20 for a tangent? Make sure you're in degree mode. Always double check that you're in degree mode. There's a chance you might have changed it.
When will you need to switch back to radians?
When would you? If it told you that the angle of elevation to the top was 5 radians, then you would have to do that. Or actually, it wouldn't be 5. It'd be more like 1 radian or something if it's an acute angle, because it can't be bigger than pi over 2. Oh, if you're in a word problem with an acute angle, just being careful. All right, 305 divided by the tangent of 20 degrees. And that means the ship is 837.98 what? Feet away. Okay, it's about that far away from the Statue of Liberty. All right, is that pretty good, everybody? Does it seem easy? Next example, number 72. Number 72. Did I turn that too fast? Everybody getting that on your calculator? Let's go to problem number 72. Okay, number 72. All right, I want you, and you can talk to a neighbor or whatever, draw it and decide on your trig function yourself. Number 72. We're finding the height of a tower. A guy wire 80 feet long is attached to the top of a radio transmission tower, making an angle of 25 degrees with the ground. How high is the tower? Draw it, set up your trig function, and go for it. Where's the 80 go? Yeah, because this is 80 feet. This is the wire that goes to the top of the tower. There's your tower. Okay, makes 25-degree angle with the ground, and the question is, how high is the tower? What trig function are you using? Sine. You got the angle. You're looking for the side opposite it. You have the hypotenuse. So the sine of 25 degrees equals x over 80. X equals 80 times the sine of 25 degrees. And we have sine 25. Multiply that times 80. And x is about 33.8 feet, I guess. Okay? Is that good? Is that what everybody got? Are you good? Oh, you can't see it? Sorry. Okay, I'm really surprised that none of these applications seem to have exact values in them. So I'm going to change problem number 72 to a number I want to use. All right, I'm going to change this angle to 30 degrees. Find the exact height. Okay, when you see the word exact on your test, means this is probably one of your special angles, so don't be trying to use a calculator. All right, so let's change it to 30 degrees. So we have sine 30 degrees equals x over 80. Now, don't look back. Let's try to think. When we have 30 degrees and 60 degrees, it's either going to be a half or a square root of 3 over 2, correct? 30 degrees, and sine means opposite. So opposite the 30 degrees, you got your smaller side. So what is the sine of 30 degrees, everybody? 1/2. So x is equal to 80 over 2, which is 40 feet. Okay? And even if it's been by your 80, and just keep your answer exact on your test. Everybody good? Is this easy? Aren't you isn't it nice to finally have something that's not too rough? All right, let's jump in section 8.1. It's the same deal again, using applications of right triangles. 8.1. We're just solving right triangles. And I'm just going to go to the exercises just to show you can do it. 8.1, I'm on page 775. Okay, and I'm just going to pick a problem like number 10. Okay, page 775, number 10. It's telling you to refer to this right triangle over on the side. Okay, so let's look at that. And then B, number 10 says we're going to tell you what B is, we're going to tell you what beta is, and you're supposed to find everything else for the triangle. Looks like exactly what we've already done, doesn't it? But let's just do it real fast. Okay, so we have a triangle. I'm following the one that's given. This is beta. Notice that angle beta is the angle opposite side B, and that angle alpha is the angle opposite side A. That's tradition. And the angle for C here is usually called gamma for some reason. That looks like this, and this is side C. Okay, in number 10, B is 4. Beta is 10 degrees, and you're supposed to find everything else. All right, I'd be surprised if you couldn't tell me what alpha is in 5 seconds. What is alpha? Beta's 10, so alpha is 80. 90 degrees minus 10 degrees is 80 degrees. Okay, Let's just use what you're given just to make sure you don't make any mistakes. So we know beta is 10 degrees and we know B is 4. All right, so if I'm looking for side C, I have the angle, I know the opposite, and I'm looking for the hypotenuse. What am I using? Not tangent. Opposite, hypotenuse. Opposite, hypotenuse. What is it?
You said opposite.
Sine.
Opposite over hypotenuse. That is sine 10 degrees equals 4 over C. Okay, then you solve. If I'm looking for A, I know the angle, I'm looking for the adjacent, I know the opposite. I have the angle, I know the opposite, I'm looking for the adjacent. I'm looking for A, so what is that going to be? Tangent. 10 degrees equals 4 over A. Got it? You just got some things to do over the weekend. Get that memorized. Everybody got that? Yes.
Is it called the law of sines?
The law of sines, yes, that's in section 8.2, and that would work. Thing is, that's not objective of the course, but if you want to use law of sines, you can certainly do it. Law of sines, if you can use it. Everybody good? All right, let's do one application out of here. Which one was it? 26. Number 26. This looks just like the section we just did. Number 26. Directing the laser beam. Laser beam is directed through a small hole in the center of this circle of radius 10. Radius 10. The origin of the beam is 35 feet from the circle. What's the question here? What is the angle? What is the angle of elevation? All right, let's see if we can figure out number 26. Number 26. Okay. Number 26. When you draw your triangle, it's going to look like this. Here's your radius of 10, correct? Your circle's a radius of 10. This is 35 feet, and it's asking for the angle of elevation. Okay. I'm looking for this angle. What trig function is that going to be? Adjacent, opposite over adjacent. What is that? Tangent. The tangent of theta is 10 over 35. But the question says, what is the angle? What are you going to do?
Inverse the tangent.
Yes, you're going to do inverse tangent.
Why are you doing inverse tangent?
Inverse says, what is the angle?
Okay.
What is the angle? So theta then is inverse tangent 10 over 35. What is the angle? Okay, anytime you're looking for what is the angle, you got to go for that inverse tangent. And I just got the signal that I'm about to run out. Excuse me?
Aren't you looking for the angle anyways? With
Well,
tangent?
sometimes they
Right.
give us the angle.
Well, when you say the tangent of 10 degrees, you know the angle, so you're
Oh.
saying tangent 10. But here we don't know the angle, so you're saying what is the angle, and you have to say inverse tangent. Inverse sine, inverse tangent, inverse cosine tells me what the angle is. Everybody verbalize it before I get cut off real fast. What is the angle? You're going to use
Inverse.
inverse of that. Okay? We'll pick up here next time. Have a great day.